Vroom, vroom. Okay, so in this practice problem 9.3 for the rotational motion section, we've got a motorcycle rider, and she's starting from rest. So from rest means that our initial angular velocity is 0. And she's going 3.75 radians in angular displacement, counterclockwise, so the positive direction, around a circular track, and it's circular because, that makes it much easier thinking about angles, in 12.3 seconds. So we've got a time here. What we're trying to solve for in this problem is what is her angular acceleration, assuming that she is accelerating at a constant rate, okay? She's not, throttling up, throttling down. She's just accelerating at a constant rate. So we've got omega I, theta, t, and we're looking for alpha. If we consult our best friend of all the equations, there is one equation that has all of these terms in it. Equation 4r on our sheet reads theta equals omega it plus 1/2 alpha t squared. And we have theta, we have omega, we have t, we have 1/2. We always have 1/2. It's just a number. It's a constant. And then we have t again, which we'll have to square. We need to solve, though, for alpha. So we can absolutely just use this equation 4r and then solve for alpha here. If we wanted to, we could kind of two-step this problem, solve for something else, like a final angular velocity, and then maybe we go and use equation 2r at that point, but we'd have to find that final first using a different equation. So let's just use 4r here. We'll get it in 1. We just have to do a little bit of math here, okay? Some people look at this and they can solve this analytically to begin with. Solving this analytically, though, is going to be a little bit annoying because we're going to have to subtract omega it, and then we're going to have to multiply an entire quantity by 2 and then divide by t squared. It's going to be a little weird. It might actually be easier for us in this specific problem to put in numbers and then to solve with those numbers in place. So if we do that, if we put in the numbers first, our theta is 3.75 counterclockwise, so it's positive. Our omega I is actually interesting because this rider started at rest. So 0. And 0 times t is 0. So this actually goes away. So maybe this would have been a little easier to solve analytically, because now all we have left is a 1/2 alpha t squared. So we just have a 1/2, the alpha which we're solving for, and then the time squared. And our time here was 12.3 seconds, which we're going to square. So it'll be a little bit more than 144. So if we wanted to solve this, we'd multiply each side by 2. Boink, boink. Get the 2 over here. And then we would divide each side by 12.3 squared. And 12.3 squared is 151.3. So it's going to get rid of all of that. So we divide by 151.3 because that is 12.3 squared. So what we'll find here is that alpha will equal 2 times 3.75 divided by 151.3, which was the 12.3 squared. So 2 times 3.75 divided by 151.3 gives us an alpha of 0.05 radians per second squared. Because radians per second squared are the units of an angular acceleration. It's an angular displacement amount, radians, divided by a time, divided by a time. So a time squared. Okay? So that problem was a little bit mathematically tricky. It got a little bit easier because we remembered that the initial angular velocity was 0 here, getting rid of this first piece. Make that a little easier. If this rider had some initial velocity to begin with, like they had a rolling start, then we'd have to do one more mathematical step. We'd have to subtract, and then we can multiply by 2 and then divide by the time squared. That's just algebra there. Nothing we haven't done before, but it was nice that this rider started from rest. So with that, this rotational motion problem is finished. Until next time, adios. and take it easy.